try off the note sheet. If you didn't end up trying those, I'm going to go through them right now. So again, this is kind of the big part of 2.7 is what I've already taught you, understanding these molecular geometries and these different shapes and the angles that they make, and how to identify them. So we're going to do 4 of them to start today. I hope you've maybe tried them or at least glanced at them. We're also going to talk about bond polarity again, which we did talk about in topic 2.1. I'll bring that back today. Yeah, and again, my hope is that today isn't too long. I've been trying to keep things under a half hour recently for very good reason, because there's no point in trying to make you stare at a computer screen for more than a half hour at a time. So, or at least that's my theory. So I hope, I hope other teachers agree with me. Anyway, so let me fire up the smartboard. Let's get rolling on 2.7. And again, if you have not, please type here in the chat, which is always the same as it is every day, but it just helps me make sure that my attendance is accurate. So, all right, let's try some of these. So again, I hope you tried these. You may have not tried these, but these are the types of problems that you're going to be expected to know how to do on my test, but also on the AP test, okay? The idea here is that I could give you a random formula of a simple molecule, because these are all simple molecules, by the way. Life gets much more complicated later in chemistry. But if I gave you the formula for a simple molecule, could you give me a prediction about the shape of that molecule? And could you give me a prediction about what angles these bonds are at? And could you name it, right? What is the name of that shape? These are all things that are a part of the AP Chem curriculum. Oh, speaking of which, you may have seen this or heard this or been emailed about it. I'm not sure what's been communicated with you guys and your families. But the window to sign up for AP testing has just opened. I believe it was yesterday that the AP testing window has opened up. So, to the best of my knowledge, I believe that you have been communicated with or are very shortly going to get communicated with by the district about how to sign up for that. It's all online, and you have between now and November 6th, which is like 2.5 weeks, I believe. So there's like a 3-week window where you can sign up for AP testing. That's not just for my class, that's for any AP class. So if you're in other APs, we are in the current window to sign up for the test. Now, I'll give you some more information later this week, and I'll probably post something on It's Learning about it too, just to kind of make sure that you're getting enough information about whether or not to take the test. Here's the deal. You're not required by any means to take the AP chemistry test. It's not a requirement. Having said that, if you signed up for this class, and if you're here, and if you're trying, and if you care, I imagine that you'd maybe want to take it. It does cost money. I think it's close to $100. I'm not quite sure if it's $100 yet. I think it's 90 something. That's what it was last year. But if you were to take and pass the AP chemistry test, you would receive college credit for this course. Okay, and there's a whole lot of questions regarding like what type of credit you would get. And I can answer those questions if you have them maybe later, but either way, I just want to make you aware, and I'll probably say this almost every day for the next 2.5 weeks. The window for signing up for AP tests is right now, and I hope that you've had some information sent home. To the best of my knowledge, you may have, or it should be coming very shortly. And anyway, think about whether or not you'd like to take the AP chemistry test. And yeah, anyway, I'll leave that for right now. We'll come back to that pretty much every day after this point too. So, all right, let's do these problems, and I'll go through them. I'm going to take a good chunk of time on these because they're kind of, again, the crux of what this topic is all about. So bromine trifluoride is the first one. I am going to give myself extra space because I can, and I know you can't, so I apologize if you have a blank sheet or the back of one of these note pages that's empty. I would encourage you to maybe find a spot to write these out, but let me go through some of these. So BRF3, that's the formula. Okay, that's that old covalent molecule naming system, right, where we have those prefixes. So tri is implying 3. Okay, so the formula should hopefully be pretty easy to find. We got 28 electrons to work with. Bromine's going to go in the middle. I have fluorines all around. Okay, that required 6 electrons. 22 left. I'm going to add these as many as I can around the outside. That's 18. I've got 4 left to go. I'll add them both to the center, both pairs, I should say, to the center. And that's my structure. Now, again, you could totally check formal charge. Spoiler alert, formal charges are all 0. We are good. Now let's analyze what we have. Okay, so what we have is a coordination number of 5. Let me recap coordination number. I hope you've been watching my videos the last couple of days, because if you haven't, you're probably going to be lost, and I would strongly recommend you go back and watch Friday and Monday's videos. They help a ton, okay? But our coordination number is how many things are we attempting to separate around the central atom. So bromine is my central atom, and around bromine, I have 1, 2, 3 fluorine atoms and 2 lone pairs. My coordination number here is 5. Okay. Now at this point, you have your sheet in front of you, right? You could totally just go to that big grid that we just finished filling out yesterday, and you could find coordination number of 5, trace over to 2 lone pairs, and boom, you got what you got. But on a test, again, it's tough for me to stop you in the digital world, but in theory, on the AP test, right, your resources aren't necessarily going to be right next to you. So you should, I would strongly encourage you to just kind of memorize that chart to a point, or again, if you memorize where the coordination number of 5 starts, meaning like what the basic shape of a coordination number of 5 is, and then you can kind of like mentally pluck 2 of these atoms off and end up with the correct shape if it was 2 lone pairs with 3 atoms, all right? Long story short, I'll go to the website in just a second, by the way, that Chem Illinois website. And if you haven't visited that personally or you know, while you're working or looking at things, I would encourage you to do so. It does help quite a bit to see the visual of these shapes. But anyway, so coordination number of 5, 2 lone pairs, 3 atoms. This is a T-shaped molecule. Okay, that is the name. The angles here would be 90 and 180. Again, we're literally making a T with this molecule, so we'd have 90 degrees in some spots and 180 in other spots. And yeah, let me jump over to the Chem Illinois website and let's see if I can do this successfully without too much issue. Oops, suppose I need to present the website. Pro tip. All right, I hope it's come up now for you. So here's your coordination number of 5 right here. All right, and if you want to bring this up on your own computer and not watch me do it, but actually bring this website up and try it yourself, you're more than welcome to. The website is on your first page of this note sheet, I believe. It's in there somewhere. Or again, if you just Google VSEPR theory, VSEPR theory models or something like that, it's going to be one of the first hits on Google. But anyway, so here's your coordination number of 5. It's called a trigonal bipyramid. We have 3 atoms around the center, or the equator. Sorry for spinning that weird. We have 3 atoms around the equator that are 120 degrees apart. So if I flip it on its end, you can see that. I've got 1 up, 1 down. So that's coordination number of 5 with 5 atoms. But that's not what we have. We've replaced 2 of these atoms with lone pairs. So the 2 atoms we're going to remove are both going to come from the equator, this one and that one. And we end up with this shape. It's a T. Okay, sorry, let me make it a T. There it is, it's a T. If I orient it the same way that I had for the first one, this is what we have. Essentially, I've removed the other 2 equatorial or equator atoms around the center, and we just get a T shape, okay? So again, the way I approach this, or the way I memorized this when I first learned it, was if I know that a coordination number of 5 starts right here, meaning 5 things separated in space looks like this, that's the shape it makes. But when I want to describe the molecule, I ignore the lone pairs, right? So I've gone from 5 atoms to 3 atoms and 2 lone pairs. So the 2 lone pairs aren't really acknowledged, but in theory, they would be over here and over here, right? They're there, but we don't use them to name that shape. All right, I can tell that this is going to take me way longer than I thought it was, but I don't know if that's a bad thing. I hope this stuff's starting to make sense. So anyway, let me represent my presentation. Sorry, it's going to be kind of clunky all hour long, but we'll manage. All right, so let me go through the next one. The next one is selenium tetrachloride. Again, we got to know what the formula is, right? So selenium tetrachloride, selenium Se, tetra means 4, Cl4. Let's go through the Lewis diagram. I'm going to go down here and just kind of find a spot that works. So Se, Cl4, total valence electrons to work with. Chlorines have 7, that's 28. When it's 7 times 4, selenium has another 6, so 28 plus 6 is 34 to work with. And by the way, if I make a mental mistake, somebody please yell at me and stop me, because, you know, I'm human. That could happen. Se is in the middle. I got 4 chlorines around the outside. That took 8 electrons. I've got 26 still to add. There's 24 of them. Oops, that's 42. We got 2 left. There you go. I'm just going very fast. Sorry for the not so neatness, but I think we've done enough of that I hope it's not too hard to follow. There's our structure of the selenium tetrachloride. If we look at the coordination number of selenium, we have 4 atoms around the selenium and 1 lone pair. This is coordination number of 5 once more. But this time, the coordination number of 5 is 4 atoms and 1 lone pair, so it's going to be a different shape than the previous one. But again, you could totally look at your grid and find the right answer if you wanted to. Let me switch back over again. I wonder if I can do this a better way. There's got to be a better way. Let's do this. Yeah, share that. Sorry, I'm talking to myself. Can you see the website? I switched back. Could you see the website? Okay, good. Awesome. All right, so coordination number is still 5. We would start mentally with this shape. Okay, we're separating 5 things, but it's not 5 atoms. It's 4 atoms and 1 lone pair. So we need to remove one of these 5 atoms and replace it with a lone pair of electrons. When you remove the first atom from a coordination number of 5, or any atom from a coordination number of 5, you're always removing these equatorial atoms, meaning one of these 3 in the center, okay? So we're going to remove one, and what we get is this shape. This is known as the seesaw shape, okay? I can't really manipulate this picture very well, but obviously you can see that this was like sort of like a seesaw, right? If I pushed on this end and it went down, the other one would go up, and so on and so forth, okay? So if I orient it the same way as the other one, all I've done is I've taken this equatorial atom away right here, right? I've removed that one. And what I have left is this seesaw shape. So for this one, we have seesaw. Where'd my marker go? There we go. All right, onward and upward. Sulfur hexaiodide. Give myself some more space. Si6. Hex, of course, means 6, right? So total valence electrons, 6 times 7 is 42, plus another 6 gives me 48. I have sulfur in the middle. I have 1, 2, 3, 4, 5, 6 iodines around the outside. I didn't leave myself a ton of space. I apologize. That required 12 electrons to set up for those bonds. 36 to go, and I'm not going to have enough room. There's 2 more over there, I swear. Hold on. Let me make it a little better. I'll try my best. I'll make these shorter. Ah! No. All right. There we go. That's 36. Round to 0. This is the correct structure. We have a sulfur in the middle with 6 bonds, 1 to each of the iodines. All of the iodines have 1 bond and 6 lone pairs. Again, you're more than welcome to check your formal charge. It's all 0. This is the correct structure. Coordination number of this molecule is 6. We have 6 atoms that are going to be separating in 3-dimensional space. The shape of that is known as octahedral. So let me scroll down, and here it is. okay? The octahedral shape is 90-degree angles every which way. All right, and again, this thing has absolutely perfect symmetry. This is my top atom at the moment, but it doesn't have to be. I could take this atom right here, flip that upward, and hey, look, it's the exact same shape. This has an insane amount of symmetry in every which direction. All right, so it's 90-degree angles all throughout. There's also, you could count 180-degree angles if you went from like the top to the bottom here. And this shape is called octahedral. Now, I haven't explained this yet, but I'll do it right now while we have a little bit of time. The name octahedral, okay, comes from the three-dimensional polygon called an octahedron. All right. Essentially, if you were to close off the face or the faces of all of these like areas, you would get an 8-sided three-dimensional object. So if you're wondering why a coordination number of 6, in other words, separating 6 things in three-dimensional space, is called octahedral, it has to do with its relation to an octahedron. Okay, octahedron. I don't know if I'm giving the wrong emphasis there. So let's look at octahedron. Here it is. So if I closed off all of the faces of here, we'll do this, or we won't. Okay, never mind. My right clicker's not working. But if you closed off all the faces of that molecule, you would get an 8-sided three-dimensional polygon, which is called an octahedron. Okay, so that's where that name comes from if you were curious, because it doesn't seem to mesh with a coordination number of 6, but that's where that's from. All right, back to where I was. So the sulfur hexaiodide is octahedral. And we got one more, arsenic pentachloride, which is AS Cl5. And I'll scroll down, make some space for myself, and go through this one. Arsenic's in the middle. I have 5 chlorines around the outside. That took 10 electrons. I'm sorry, I didn't even get my electron count. Bad teacher. All right. Arsenic has 5. Each chlorine has 7. So 7 times 5 is 35, plus another 5 is 40. All right. I've used 10. 30 left to go. There you go. That's all of them. That's my shape. That is correct. All the formal charges are 0. It's happy. Now, coordination number is 5. I have 5 atoms separated in three-dimensional space, and that's going to be that basic shape for coordination number of 5, the top one here. This is called trigonal bipyramid. Where does that name come from? I already told you this in the video, but let me give it to you one more time. If I flip this on its side, you'll notice around the equator, we have 3 atoms perfectly spaced, 120-degree angles between these. All right, it's a triangle. Now, when I flip it back up the way I had it, I have a pyramid to the top and I have a pyramid to the bottom. You could visualize this as, okay? So trigonal implying the 3 around the equator, bipyramid implying a pyramid towards the top atom and a pyramid downward towards the bottom atom. It's a weird name. It's not the best name, but it is what it is. So let's name this, and then let's actually teach you a new thing or two in the next 10-ish minutes. So a trigonal bipyramid. All right. So again, if you didn't watch the last 2 videos, I have a hunch the last 20 minutes of this class did nothing for you and it was very confusing. Please go watch the last 2 videos. Or if you just kind of didn't quite hang with what I was up to right there, I would encourage you to maybe go back and watch a little bit here and there, get a little help. Stop into my office hours and try to understand this stuff, because this is kind of a big deal and it's definitely a part of your AP tests if you so choose to sign up for that. Of course, it's a part of my unit test, I should say. That's guaranteed whether or not you sign up for the AP test. But anyway, all right, so let's use this knowledge just a little bit and switch gears and kind of tie back in a concept that we started this unit with, okay, which is on polarity or polar bonds. And again, we might have to refresh just a little bit with that, but I'm on to the next page now, okay? So I have some examples and I have some directions in the top there on what I would like us to do. So in this first example here, I want us to draw a molecule with this formula. The formula here that I want to work with is this guy, okay? SBr2Cl2F2. So a sulfur in the middle with 2 bromines, 2 chlorines, and 2 fluorines around it, all right? I'm not gonna make us do the Lewis diagram. I'm not gonna make us figure out the geometry because I'm giving that to you, all right? I want to go and look at something else related to this topic. So this is an octahedral shape. You can kind of see that I have that little picture put in right over here. So the question, or what I would like us to do, is use this and draw a molecule that has polar bonds, but overall is not polar. So let me explain this and talk about this a little bit and go through what the heck that means or what I'm asking for. All right, so first thing first, sulfur's in the middle. Okay, and I am going to try my best to draw a 3-dimensional picture. Again, it's not going to be pretty, but hopefully maybe a little bit you can visualize what I'm up to. Okay, so polar bonds. Let's talk about polar bonds from back in topic 2.1. Now, polar is implying a positive region and a negative region, or a positive end and a negative end in chemistry. So when I say a bond is polar, I'm implying that one of the atoms of that bond is partially negative charged. The other atom in that bond is partially positive charged. Now, these partial charges, or the polarity, comes from the fact that these atoms have a different electronegativity. Electronegativity, just to bring it back because it's been a while, electronegativity is a value of how strongly an atom will attract bonding electrons towards its nucleus, okay? So we had numerical values for these, and I had a dumb mnemonic for you, which is phone Chloe, bro, FONCLBR. Those are the 5 most electronegative elements. Those 5 elements, fluorine, oxygen, nitrogen, chlorine, and bromine, attract shared electrons or bonding electrons very strongly towards their nuclei. And as a result of that attraction, the electrons are pulled towards them and they end up getting partial negative charges, okay? So here's the deal. I can have a molecule where the bonds between any 2 atoms in that molecule are polar, meaning the electrons are not shared equally. But I can arrange the atoms in this molecule in a way where essentially they cancel each other out, and the overall molecule as a whole, when I take into account all of these individual bonds, ends up being nonpolar, meaning it's all perfectly symmetrical and it cancels out. I just gave you a lot of words and a lot of refresher. Let me show you what the heck I'm talking about a little bit. Okay, so I'm going to put a fluorine up above and a fluorine down below. Okay, again, the shape of this molecule is octahedral, right? So this is what I'm going to end up with for a 3-dimensional picture. If I put one fluorine above and one fluorine below on completely opposite ends of each other, here's what happens. This bond up top, okay, is polar. The fluorine is more electronegative than the sulfur, and these electrons in that bond are being pulled upward towards the fluorine atom. On the opposite end of this molecule, I have a fluorine on the bottom. The electrons in this bond are being pulled towards the fluorine down on the bottom bond. And as a result, this fluorine would be partial negative and the sulfur would be partial positive. because of the way these bonds are angled and the way and where I've put these atoms, this fluorine is pulling upward on the electrons based on its electronegativity. This fluorine down here is pulling on the electrons downward based on its electronegativity. And they're on completely opposite ends of that molecule. And as a result, they completely negate one another. They pull with equal and opposite attraction to the electrons, right? And as a result, it's perfectly symmetrical and they cancel out. It's kind of like vector math, if you've ever done vector math. And I know for some of you, that's not a positive memory to bring back. And others of you, maybe you have not done any vector math, okay? I think it's a pre-calc thing. I could be completely wrong. I can't see your faces, so I don't know. Either way, it's if you account for one force pulling upward and another force pulling downward, if it's equal and opposite, they cancel. And that's what we have going on here, okay? So let me add the other atoms. I could add the two bromines. I'm going to add them to opposite sides of my three-dimensional structure. I'm going to add a bromine coming outward towards you, right there, and another one going back away from you right there. Again, I'll show you a real 3D picture in just a second because it's going to do way more to help you see it than my picture will, but these are on opposite ends of the molecule. This bond is being pulled towards that bromine because of its higher electronegativity. These electrons in that bond are being pulled towards that bromine because of its higher electronegativity. But these are on completely opposite ends of the molecule, and they're pulling equal and opposite direction. They cancel out. The last ones I have to add are the chlorines. I need a chlorine going out towards us in this direction and another chlorine going away from us in that direction. Same sort of concept, right? The chlorine is more electronegative. The electrons in those bonds are being pulled in equal and opposite directions, and as a result, they completely cancel out. This is an example of a molecule that has polar bonds, meaning if you look at every one of those 6 bonds, the electrons of those bonds are not shared equally. The electrons of every single one of those bonds are being pulled outwards towards the more electronegative atom. But the net result, once we consider all 6 of them in conjunction, right? The fluorines pull equal and opposite. The chlorines pull equal and opposite. The bromines pull equal and opposite. They all cancel out. So we have polar bonds, but a non-polar molecule as a result of where these atoms are all located in this three-dimensional structure. I feel like it just got super dense in the last 10 minutes, but let me just recap what I'm up to and we'll call it a day, okay? So here is that three-dimensional picture, right? This is the one we're looking at. We have the octahedral shape. And what I've done, sorry, I'm trying to fight this. It's for whatever reason, it doesn't spin very nicely. But anyway, so what I have is I have a fluorine up here, a fluorine down there. Equal and opposite, they cancel out. I have a bromine right here, a bromine back there. Equal and opposite, they cancel out. Chlorine, chlorine, same thing, equal, opposite. They pull completely in opposite directions and it's equal strength of attraction and it all cancels out. Okay? I don't know how I did today. I hope it was okay. Again, we're not making much progress because I'm really trying to hammer home the concepts of, of these three-dimensional shapes. At the very least, I'm gonna kind of go deeper down this rabbit hole in the next couple of days in terms of some more concepts related to this. But at the very minimum, I hope you can start to have some confidence with drawing an appropriate Lewis diagram, and then from that appropriate Lewis diagram, predicting or giving me the three-dimensional geometry, molecular geometry of that shape. Okay? All right. I'll leave you guys alone. If any of your parents are coming to talk to me today, awesome. If not, I wouldn't mind talking to parents. That's a good thing. That helps you do well, I think. Maybe not, I don't know. Maybe you don't want your parents to talk to me, I'm not sure. But either way, have a lovely evening. If you need me, don't be shy, please reach out. I'm happy to help you. AP testing window is open. Please consider that and think about maybe what you'd like to do for the test. Yeah, and I'm all done. Have a lovely day. We'll see you guys tomorrow.